Have you ever tried to move a heavy rock or log with a lever? If so, you have used a second-class lever. The fulcrum of the lever is the point where it touches the ground, and the load, the rock or log, is between the fulcrum and the point where you are exerting the upward effort. As with a first-class lever, the distance of the load from the fulcrum determines the mechanical advantage. If you want to move a very large load with a small applied force, you must put the load very close to the fulcrum. You use the same formula to estimate mechanical advantage for second-class levers as you do for first-class levers. A wheelbarrow is a good example of a second-class lever. When you lift the handles of the wheelbarrow, input effort, the load, resistance that is located between the effort and the fulcrum moves up. A nutcracker and a jar opener are also examples of second-class levers. Because the fulcrum is at one end, the applied force is at the other, and the load is in between. Third-class levers. With third-class levers, the fulcrum is at one end of the lever, the load resistance is at the other end, and you apply the effort between the fulcrum and the load. Third-class levers always multiply distance and speed without changing the direction of the effort. That means the lever will always push the object farther, or faster, than the effort force. Examples of a third-class lever include a baseball bat, yard rake, and broom. Figure 7.8 illustrates how a third-class lever works. Resistance/load. Because the effort is greater than the resistance, this type of lever gives you a mechanical advantage of less than 1. Therefore, the effort must always be greater than the resistance. To find the mechanical advantage, use this formula. MA equals effort arm resistance arm. So if you place a 50 pounds load 4 feet from the fulcrum, and you are exerting effort 2 feet from the fulcrum, MA equals 2/4, or 1/2. That means you have to exert 100 pounds of effort, or twice as much effort as resistance, to move the load. Wheel and axle. Essentially, the wheel and axle is a circular lever that rotates around a center point that acts as the fulcrum. The arms are the radius of the wheel and the radius of the axle, see figure 7.9. And are unequal in length, meaning that the wheel and axle are different sizes. The larger, outside wheel rotates around the smaller, inside wheel, the axle. When the wheel turns, the axle also turns, and the axle multiplies the effort applied to the wheel. 50 pounds. 100 pounds. Although the effects of friction impair the overall efficiency of a wheel and axle, as compared to a lever, you still don't need to apply as much force to move a load as you do with a lever. However, you apply the effort over a greater distance from the fulcrum, compared to the distance of the load. The wheel and axle combines the effects of both a pulley and a lever by redirecting the force applied through a rope or cable and increasing or reducing the magnitude of the force. You can apply the effort or resistance on either the outer wheel or the axle. Depending on where you apply effort and resistance, the wheel and axle can multiply force or multiply speed. You can calculate mechanical advantage by using this equation. MA equals input radius output radius. You can use the inverse of this ratio to determine the effort needed to balance the load as well as the distance. MA equals load effort. In figure 7.9, the axle radius is 4 inches. And the wheel radius is 8 inches. You can determine the ratio between effort and load. A 50 pounds force applied to the wheel will balance a 100 pounds weight suspended from the axle. The mechanical advantage of this machine is 2. The weight of the object is twice as large as the force required to balance it. Examples of the wheel and axle that multiply force are a doorknob, a winch, a windlass, and the pedals and front sprocket of a bicycle. Examples that multiply distance and speed are the rear wheel and sprocket of a bicycle, the blade of a lawnmower, and an airplane propeller. Pulleys. A pulley consists of a belt, rope, cable, or chain wrapped around a single, grooved wheel. Depending on how it is arranged, a pulley might or might not multiply the effort. A pulley reverses the effort force applied to the rope. If you have a pulley system, the smaller pulleys will turn at a greater speed than the larger pulleys. You might see 3 pulley configurations: a fixed pulley, a movable pulley, and a block and tackle. Fixed pulley. A fixed pulley does not move with the resistance, and does not multiply effort, but it does change the direction of the effort, as figure 7.10 shows. It has a mechanical advantage of 1, and work output always equals work input. Effort. Movable pulley. A movable pulley attaches to the resistance and moves with it. This type of pulley multiplies effort, but does not change the direction of the effort, as figure 7.11 shows. A movable pulley enables you to apply an effort, discounting friction, of only half of the resistance force, but you must apply the effort from twice the distance as you want to move the load. For example, although you would exert a force of only 5 pounds to raise a 10 pounds box 2 feet with a movable pulley, you would have to pull 4 feet of rope through the pulley. Calculate the mechanical advantage by dividing the effort distance by the resistance distance, or MA equals effort distance load distance. Block and tackle. A block and tackle, also called a pulley system, is a combination of one or more fixed pulleys and one or more movable pulleys. In a block and tackle, the movable pulleys multiply the effort force, while the fixed pulleys change the direction of the effort force. Figure 7.12 shows a block and tackle system. A block and tackle provides considerable mechanical advantage, because it increases the effort by the number of times the force changes direction. You can increase the number of pulley wheels to get a higher mechanical advantage. By counting the number of ropes that support the resistance in a block and tackle, you can easily determine the mechanical advantage. In figure 7.12, a block and tackle with 4 segments of rope supporting the resistance multiplies the effort force by 4. Thus, the mechanical advantage is 4. That means if 4 segments support a resistance of 20 pounds, you must apply an effort of only 5 pounds to the rope to raise the resistance. Effort equals R/MA. Effort equals 20/4. Effort equals 5 pounds. Effort 4 feet. Effort. Resistance 2 feet. 10 pounds. However, that means you must also pull the rope 4 feet for every foot you move the load. 5 pounds effort. Ma equals. However, that means you must also pull the rope 4 feet for every foot you move the load. 5 pounds. Exam alert. When calculating effort, remember to count the segments of the pulley system, and use that number to divide into the load weight to determine the amount of effort that you need to apply. If the question entails a bosun's chair, pay attention to whether the chair itself has 2 segments of rope, see figure 7.13. Figure 7.13 Bosun's chair. Inclined planes. An inclined plane consists of a sloping platform that allows you to use smaller effort to raise a load by providing for a gradual climb, as figure 7.14 shows. To raise a load vertically, you must instantaneously apply a force equal to the weight of the load. 80 pounds. Although using an inclined plane is slower than using a vertical lift, you can apply an effort smaller than the weight of the load to raise an object. The longer the ramp is, the less effort you must exert at one time. Although lifting a load straight up requires more force over a shorter distance, in the end, you do the same amount of work in either approach. To calculate the mechanical advantage of an inclined plane, you divide the length of the incline. Effort distance, by the vertical rise, resistance distance, called a run-to-rise ratio. Although the mechanical advantage increases as the slope of the incline decreases, the load must be moved a greater distance. To find the mechanical advantage of an inclined plane, use this formula. MA equals effort distance resistance distance.
Don't forget to subscribe.